Hello guys, so in this video I will be discussing about the SARIMA modeling. Basically it is the seasonal ARIMA model, which is Autoregressive Integrated Moving Average with seasonality. So let's begin. Let's start importing the libraries pandas, numpy, matplotlib, stat models, and import OS for changing the directory. And the data which we are using is Superstore, which you can download from the Kaggle. And basically pandas is for pandas data frame, numpy for multi-dimensional data. It can be a one-dimensional vector, two-dimensional matrix, or three-dimensional. And then for visualization we will be using matplotlib. And then a stats model package is used for ARIMA and SARIMA modeling. So we are filtering the warnings, and we want to ignore if there are certain warnings which are not very significant for us. So we do not want to print it. For that reason we are just writing like this. So let's begin. Now we are reading the data. It is an Excel sheet, so we will be reading the data. Then let's look at few rows of this data. What we want to see is you can see the column categories. So it has furniture, office, supplies, and basically this is as orders. These are orders and these are customers, and they have ordered from these countries and these cities, postal code, region. So we are not basically interested in which order, which country, which city, but we are basically using basically we will be using the category and the sales. So we can see the order date, because we are going to discuss about the time series predictions, forecasting for the future dates. Basically we will be using for monthly data, but here it is given the daily data, which is like 2016 and November 8, then June 12, like these. So these are daily data. So we will be converting this daily data into monthly data, and we will group by this category, and we will take one category, and then we will try to predict the sales, monthly sales for each of these categories. But basically we will take any one of these categories to show that how we can fit a SARIMA model on this. So let's see what categories are available. So we can see from this data category dot unique. So these are the categories which are available in this data: furniture, office supplies, technology. So, and then we can group the category. So we are grouping the data by category and seeing what is the observations count for each of these categories. So we see, then for furniture we have this much of data, 21 days we have, and for office supplies we have 26 days of data. Like this we have for technology also we have this much of data. So we will be filtering the category. We will be taking the furniture for this tutorial, and then let's filter it. So data we are filtering by category as furniture, and then we are sorting the values by order dates, and then let's see what we get. So we can see that the order dates are now arranged in the order. So 2014 January, we see the dates 6, 7, then 10, then 11, then 13. So these are ordered by the dates. Now we want to take only those columns which we are interested in. So definitely we are interested in date, we are interested in category, which we have already filtered all our furniture. Now we don't have any supplies, we don't have any office supplies or technology. Now we only have furniture. Now we can see the furniture, and we have the sales for the daily sales. Now we want to predict the monthly. So for monthly we have to group this daily data, and then we will be group it and then get the monthly sales for each of the month in all the years. So let's see what we can do now. So now we can see that if we are just taking these columns, just a moment. So we can see that we are taking only the columns which have order date and the sales, and then we are resetting the index so that we have the columns as order date and the sales. Let's do this. Now we can see that 2014 January 6, 7, 10, 11, 13. So these are ordered date for the furniture category only. For daily we have the sales, and now what we will do is we will take the monthly data. Out of this data we will group it and get the monthly data. So df dot group by order date, grouping by order date and sales and sum. So first before getting the monthly data, we will be, what we are doing is we are taking the, if we have any daily for a given date we have many sales, 2 or 3 sales, then we are adding all those sales so that we get the accumulated sales on a daily basis. That's the reason we are just doing this thing. Now again we got this thing, since it was already mostly for one day it was already aggregated, so we are having the same kind of data again. So now we are setting the index order date so that we can resample it by monthly. So we have already set the index order date, and now we can just write that this df sales, and this is the sales category, this is the sales column, and then we are resampling by monthly data and we are doing the mean of it. And that means for a given month, like say we have 30 days, and for each of the days we already have the data. For all those 30 days we are calculating the average for all those 30 days. So on we can say this is the average monthly sale, average monthly sale we are having. So we can see now what we are having. So we can see this is Y. So this is the column which we want to predict, 480, 367, 857. Now we can see this is for January, first one, then Feb, then March, then April. So for first we have 480 sales, 480 units of sales, and for Feb we have 367 of sales. We have basically aggregated, we have taken the average for 30 days and get for each of the month. That's what we have done in this line of code. Now what we will do is we will just see the data again. We can see this kind of data. We have some kind of seasonality in this. So if you see in January we have a dip mostly in Jan, and just before Jan we have peak, which is like from Jan to December it is going upwards. So here Jan to 2015, and then this is 16. So again we can see there is an upward trend from Jan to December, and then again in January it falls again. So January to December it is an upward trend, and then it again falls to January. So now what we are doing is we will be splitting the data before, and this is very important so that we can validate the model. Otherwise what we are doing is we take all the data, we fit the model, and then we are kind of overfitting because the model is learning from all the data. So that's the reason we will separate the testing data set on which we will not be fitting the model, on which we will only test the model accuracy. And in such a way we will be learning only from the training data set and not from the testing data set. So what we have done, we have just taken the last 11 months to predict as testing data set, and rest of the beginning of the data, that means January 2014 till January 2017 we are taking as the training data set, and from Feb 2017 till December December 2017 we have to predict. That is the testing data set, and that's what we have done in this line of code. We can see few rows of the training data set. First one was like we are seeing the last few rows of this training data set. This 2016 December and then 2017 Jan. Till this we have taken the data in the training data set. Now let's see the training data set, how it looks like. So it looks like this. From January 2014 we have January 2017. We can see we have the dips in January. In each of these January we have the dips, and in December we have the peaks. You can see, so Jan to December we have a clear upward trend. In between there is a dips and ups coming in between, that we have to model as best we can do using the SARIMA model. Similarly, we can see the y-testing plot, and we see from Feb 2017 till December 2017 this is a separate dataset, testing dataset, which we will not be touching while we are fitting the SARIMA model. So before begin, there are a few steps before fitting the SARIMA model. There are a few steps which is like AD Fuller test, and this test is necessary to check the stationarity of the series. Sometimes the just differencing of the series doesn't work for making the series stationary. For that reason, we have to perform some kind of transformations. These transformations could be like taking the square of the series or square root of the series, or maybe taking the log, or maybe taking the exponential. You have to do something so that the series becomes stationary. And stationary, we mean to say like this: we have the series, we see that here the mean is somewhere here also we have the mean here, and here also we have mean. So mean is not changing a lot, though we have a variance which is changing a bit. So we should have the constant mean and constant variance. That is the condition for the stationarity, and for ARIMA model it is very necessary to check this thing, so that if it is not stationary, we can do some log transformation or something so that it becomes a stationary. And here we can see there is a bit of stationarity in the series, and mathematically we have to check it using AD Fuller test. We have already imported AD Fuller in the imported libraries. Let's see the results of this. We are fitting in this first line of code to the training data set AD Fuller, and then we are seeing the statistics ADF, statistics p-value and critical values. So if you print it like this, you get the p-value. You have to see the p-value. If the p-value is very close to 0, that means it is a positive test in the sense that the series is stationary. Otherwise, if the p-value is something close to 1, or maybe 0.5 or 0.4 or 0.3, that also is not very significant to say that the series is stationary. For that the reason means usually you should have 0.01, 0.002, something like that, so that before you can say that the series is stationary, and you can move ahead to fit the ARIMA or SARIMA model. So we are sure that this series is stationary. We don't have to do any kind of transformations in this series. Next we will be using the next step is to see that if we can use the ACF and PACF. In ACF is autocorrelation factor, and PACF is partial autocorrelation factor. Basically, we have a series. We create like one series. That means we just shift it by 1, or series, or shift it by 2 time steps, and then you try to correlate. Means you have series, and then you try to correlate with the series just 1 time step ahead or back. You have to see what is the correlation in between these two series. Or the purpose of seeing this is to see if we can predict the future point by the past value or not. If only many of these things are happening in the past, means you are able to predict the future by the just lag 1 value. That means just previous value, just previous 2 values, that is the lag 2, just previous 3 values. If you can predict that is the lag 3, that means you have some autocorrelation in the series. That is the purpose, to see which lag is important, lag 1, lag 2, lag 3. And also you can just have a hint that whether it is a AR1, AR2, or whether it is a moving average model, or it is a ARMA model, or if there is any kind of seasonality. So let's see. So here if you see in 12, 10, 11, 12, you have seen there is a significant peak, and in the PSCF also. PSCF is actually only the component of individual lags, whereas in the ACF, if you see the lag 3, this is lag 1, lag 2, lag 3. Lag 3 is not just the component of lag 3 only, it is including the effect of lag 1 and lag 2 also. That is that it is cumulated autocorrelation, whereas the PSCF is individual contribution to the correlation factor. So in the lag 12 that means there is any data point, if you want to predict, you can predict it by going past 12 values in the monthly data, and using that data you can just predict the 12 months future. So you can just see the current date, current month, just see the current month and go back 12 months back, see the value, and then you can predict the future. So we assure that there is a 12-month seasonality here, and any lag is not significant enough. We can say that lag 1, lag 2, these are not very significant, but we can say that we can go ahead because there is like a exponential decay in both of these. So there is nothing weird happening in this charts. This is just to visualize that what kind of lags are important, so that you can use AR or MA. Now we will just decompose this complete training data series and into trend and seasonality and the residual component, which is sm.tsa. This is the package, and your seasonal decompose is the function method which are fitting on Y training dataset, and you're using the additive model. So if you see now, there is a trend, but trend is going upward, downwards, but you can say that there is a not a specific trend. You can say that it is going upward or downwards. And the seasonal component, we can see there are peaks in between, and there are homogeneous kind of peaks we have, and this is the residual component. So trend, seasonal plus residual gives the original series. The purpose of this is to again see if what kind of trend is there. Is there any kind of upward trend, if there is any kind of seasonality, and what is the residual. Now we will be using this SARIMA model since we have the seasonality. If we were not having the seasonality, we would have used just ARIMA. Since we have seasonality, we are using the seasonal ARIMA, which is SARIMA model. ARIMA, which I already told, which is Autoregressive Integrated Moving Average. Integrated is used for differencing the series. What kind of differencing should happen in the series so that the series becomes stationary just by differencing by the lag 1 or lag 2 or lag 3. Autoregressive is just you are trying to regress over the past values, and moving average works on the forecast errors which has happened in the past. Now ARIMA model itself has only 3 parameters, which is P, D and Q. P corresponds to autoregressive, Q corresponds to moving average, and D corresponds to integrated, which is the difference part. When you have the seasonal ARIMA, it has 7 parameters, 3 for ARIMA, which is already P, D, Q, and 4 for seasonal component. So 4 out of 4, these 3 are again P, D, Q, but it is for the seasonal part, and 1 is for the seasonal frequency. So since we have already seen there is a 12-month season, so the seasonal frequency here is 12. So we will have P, D, Q small for ARIMA, capital P, capital D, capital Q for seasonal part ARIMA, and then the 4th component of the seasonal is the period of the season, which is 12. So now we can see what we want to see how this SARIMA model will look like. So we are choosing three parameters P, D, Q. Now we are taking 0, 1 and 2, and then we are iterating, we are creating the products of P, D, Q. Product, I mean to say, we are creating the combinations of P, D, Q. It's showing like here 0, 0, 1, 0, 0, 1, 0, 1, 0. These are combinations of ARIMA first tuple, and the second tuple is this first row. If you see, this is one SARIMA model, this is second SARIMA model, this is third SARIMA model, this is fourth SARIMA, and this is fifth SARIMA. These are just you can say that these are different models with different parameters, and each of these model has 7 parameters. First 3 is for ARIMA and the next 4 is for seasonal part. This is small p, small d, small q, and then this capital P, capital D and capital Q, and then 12 is the frequency, which is the same for all the SARIMA, because we have already seen there is a 12-month seasonality. So this is just to see that what kind of SARIMA model we can have. But since we don't know what PDQ, what capital PDQ should be, so what we will be doing is we are creating the loop for different combinations of PDQ small and capital PDQ capital, and then we will see that which of these model have the lowest AIC. AIC is the metric. We can say that it is like an accuracy, RMSE or something, but this is the metric which we have to see. It should be the lowest AIK information criteria. First, what we are creating a dictionary of metric AIC. So this will be storing for all the SARIMA model, we will be storing the AIC metric for all the combination of SARIMA parameters, 7 parameters. And we are iterating first for loop for the small PDQ and the second for loop for capital PDQ, and then we are trying this model SMTSA status space SARIMAX. So this is the basically model which is seasonal ARIMA fitting on the training data set, and the order which is for ARIMA PM, and this for the seasonal part. These are the combinations of 4 parameters, and then we will be fitting this model, which is now model underscore AIC, and then we are printing this combinations of ARIMA parameters and the seasonal parameters, which are 7 parameters, and also looking at the AIC of each of these models which we are fitting, and then we are storing these parameters and the AIC. So if you run this, you can see this is running. So we can see first ARIMA model 0, 0, 0. This is for ARIMA and this is for seasonal part 0, 0, 0, 12. So first one has small p, small d, small q or 0, capital P, capital D, capital Q or 0, and 12 is the frequency of season, and the AIC is 588. We have so many models we have created. We can create more by changing the PDQ values, as we have taken PDQ only 0, 1, 2. You could try for 0 to 10. You can choose as you wish, and then the purpose is to see which one is the lowest. And how you will see is just this line of code. If you run this, you will see which one is the lowest. Basically here we are sorting the dictionary which we have created by the values, which is the AIC, and now we can see that this one, which is this one, there are NA values. For that reason this is showing here, but from here if you see 153, 154, like this, and it is increasing and increasing and increasing. So this one is the best, 110, 110, 12. So small p 1, small d 1, small q 0, then capital P, capital D, capital Q, and then 12. So we will be using these combinations for the SARIMA model. Earlier we had just tested which of the combinations could be best on the basis of AIC. Now we will be fitting this parameters. Now we see 110, 110, 12. So what we will do, 110. So again we are using the same model which we have used in the inside the loops. sm.tsa.status_space.sarimax fitting on training data set, and the ARIMA orders a small p, small d, small q. Seasonal parameters 110, where these are capital P, capital D, capital Q, and then the seasonal frequency, which is 12. This is the model, and then we are fitting and then creating this fitted model underscore AIC. You can see the summary here, and 3 points to 110, 110, 12. So what we will do, 110. So again we are using the same model which we have used in the inside the loops. sm.tsa.status_space.sarimax fitting on training data set, and the ARIMA orders a small p, small d, small q. Seasonal parameters 110, where these are capital P, capital D, capital Q, and then the seasonal frequency, which is 12. This is the model, and then we are fitting and then creating this fitted model underscore AIC. You can see the summary here, and 3 points to keep in mind of 3 and 4. So first step is to fit the model. This is the model, this line of code. This line of code is the basic thing which you have to fit in that second line. So this will give you model underscore AIC. From model underscore AIC you can get the prediction, which is the forecast, and from this forecast you have to use forecast.predicted mean. These are the final predictions which we'll be using for plotting or for calculating the RNSE or everything. And from forecast only you can get the confidence interval also, means how accurate you are sure you're about your forecast, 95% sure or how much sure you are. So first you have to write this model, and then you create model underscore AIC by fitting, and then you create forecast from the same model underscore AIC dot get prediction, and from that forecast you will be using the predictions and confidence interval. Forecast.predicted mean is the predictions, forecast.confidence interval will be the confidence interval. Just remember these lines, and then everything is easy. You can just see here. You can see autoregressive lag 1, which is the ARIMA model, and seasonality lag 12 is important, autoregressive, and sigma 2 is basically the variance of the residual part. This is the we have only two components here. Where AR component, which we can see here, we have AR component, but there is no MA component. Moving average component is 0, and moving average component of seasonal part is also 0. But there is difference in part in both. ARIMA also, and the seasonal part D is 1, and here also capital D is 1. Which one? This one. So basically internally this model has difference for both of these, for the lag 1 and for the lag 12. Okay, and the residual part is the sigma, which is the residual part which the SARIMAX would not be able to model it, and that is the variance which we can see here. This is the variance, and now we can see the p-values. These are the p-values, and these are the coefficients, means this times this plus this times this plus this times this gives the final series. Now if you want to see the diagnostics of the model of the residuals, so you just write to model underscore AIC, which is this one, and then you write plot underscore diagnostics. If you just do this, you see you have now all the plots for the residuals part. No trend, no seasonality, only the residual. In the distribution here you see it is almost normal, which should be. If it is not normal distribution, definitely these residuals have certain patterns which you can try to model using different methods. And in the ACF part also you see that there are no lags which you can now use to predict the residual part, which are significant. This is the 0, which is always 1. The lag 1, lag 2, lag 3 all are insignificant, which you can see in the blue line. All are below these, and none of these are coming outside of this blue region. Now if you see QQ plot also, it should be the straight line with 45 degree, and it is almost. And in the standard residual, The variance of the residuals should be constant. So it is, you can see that it is not varying a lot. This is around 0, and there is no such pattern which we can see here, which we can try to predict. Means it is almost normally distributed, which you can see in this plot. So residuals, you can see there are certain negative residuals, there are certain positive residuals, and you can see their density. So it is almost normally distributed. So all these plots, this one it is showing the distributions, like which one is the negative residual, which one is positive residual. It is showing the distribution of negative residuals at the positive, and it is normally distributed. And then this is the QQ plot, which is should be a straight line. It is also again trying to show that it is the quantile of all the residuals are uniformly distributed across the whole distribution of the residuals. Calculating the forecast, as I already told you, model underscore AIC dot get underscore prediction, and you give the date 2017 Feb, because that is the testing data set. Then you get the predictions from the forecast using forecast.predicted mean. You already have the actual values for the from the testing data set, which starts from Feb 2017 till December 2017, and then you calculate the RMSE by differencing, squaring, differencing this predictions and actual, squaring and taking the average. You see, you get the RMSE of 294 here. Now what we will do is we will use the get underscore forecast for the next 12 steps, and you get the predictions from the forecast, which is predicted mean, and then confidence interval from the forecast by using conf underscore int. And then this is the part for plotting this y, which is the actual complete data starting from 2014 January till December 2017, and here you are using the confidence intervals, and then on top of it you plot the prediction plot, which are the predictions for the testing data set, for which we have not used in the modeling. We have only used the training data set, which is the y underscore train. You just do this and you get the prediction. So you start from 2014 January, you go 2015, and you see there is a dip. Before 2015 there is December, which is a peak. 2016 January there is a dip. Just before it there is a peak. In 2017 there is again a dip, January, and just before it there is a peak. And then these are the prediction part which we have done from 2017 till 2017 December. We can see 2017 there is a dip in January, and in the December there is a peak. So predictions are these one, starting from here till there. In 2018 again there is a dip coming in the predictions, because this is a January 2018. Thanks for watching this video. You can subscribe, like and comment if you have any doubts. Thank you.